Okay, so let's start 6.4. And 6.4 is about the fundamental theorem of calculus, part 1, which says if f is continuous on the closed interval ab, then the function capital F of x is equal to the integral from a to x of f of t dt, or then that function has a derivative at every point x in that closed interval a to b, and the derivative of capital F with respect to x is equal to d by dx of the integral from a to x of f of t dt, and that's going to be equal to little f of x. So this basically gives us the relationship between derivatives and integrals. So I'd like to start by going through the proof, because I think it brings a lot of important things. So we're going to start with the definition of a derivative. So if I'm taking the derivative of capital F with respect to x, and you need to be careful here and make sure that you're making your capital F's and your lowercase f's look different. Okay, we've talked a couple of times about how writing math and writing calculus is about writing a different language. So by definition, this is the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, and that takes us back to that formula that we had about taking a slope, right? And that this was the slope of capital F of x between x and some point really close to it, which was x plus h. And then what we're going to do to find the derivative is make the separation between those points be really, 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 really small. No, but so would you do me a favor, please, and bring me the hand sand from back there so I don't infect everything else? Okay, so we're going to substitute in for capital F because we have a definition for that. So I've still got my limit as h goes to 0, but I've got my integral from a to x plus h of f of t dt, going to use my dummy variable here, minus my integral from a to x of lowercase f of t dt all over h. So remember, what does an integral really mean? Area under the curve. So let's look at these two integrals for a minute and compare them and see what that difference is going to be about. So to make this easier to illustrate, I'm just going to pretend that f of t is a straight line. It'll work for anything, it's just a little easier to see if f of t is a straight line. So here's going to be a, here's going to be x, here's going to be x plus h. Okay. What, buddy? Okay, then you can be on your YouTube. Yeah. So my first integral up here that goes from a to x plus h is going to be all of this area, right? Bless you. You too are falling. Okay, but then the integral that I'm subtracting from it from a to x is just this part here. I'm just finding what, Zoe? The integral. So when I take the green area minus the blue area, what I end up with is this part here. And that's just the area from x to x plus h of f of t dt. Everybody see that? All right, we good? Everybody got what they need? So, again, I have df dx, limit as h goes to 0. And now the difference between my integrals has become the integral from x to x plus h of f of t dt. Does anybody know what that is? Anybody know what's in the brackets? What if I pointed that out? Oh, it was for no good reason. What if you rewrote h as this? X plus h minus x, the upper limit minus the lower limit. 1 over b minus a, perhaps, times the integral from a to b of f of t dt. It's the average value. Okay. So this is the average value of f. And the mean value theorem, you knew there was a reason why we learned that. The mean value theorem tells you that if I take the integral, take 1 over h times the integral of x to x plus h of f of t dt, that has to be equal to f of some value c. Yes? If it's a continuous function, that at some point on that interval from x to x plus h, the function itself has to take on the average value, right? That's what the mean value theorem says. You may ask yourself why we're going to do that, but there is a reason. All right, you with me? You got it? Nothing too scary so far. So again, I have df dx. My limit is h goes to 0. I've got 1 over h, my integral from x to x plus h. Whoops. F of t dt. That's the average value. The mean value theorem tells me that my function has to take on the average value at some point C, where C is on the interval. So C is going to have to be between x and x plus h, right? Now what? What do you think I'm going to do next? Nope, because I don't really know what f is. It's just some random function. Well, what haven't I done yet? What operation, what thing up there have I not addressed? Nope. That's what I'm trying to find. The limit. So if I focus on the limit here and I let h go to 0, what's going to happen to c? Oh, no, not going to be 0, not going to be negative. It's going to be equal to x. If I take my limit here as h goes to 0, and this is not a real equation, so don't take it to one of the math teachers, okay? If we take the limit as h goes to 0 of my little inequality over there, then let's review for a moment here, lest you forget. When you come to a limit, there are 4 or 5 things that you do. What's the first thing you do when you come to a limit? And you have to evaluate it. You could graph it. That's not the first thing you should do. You could graph it. What? Plug in, which is what we're going to do in a minute. What else do you do? Simplify if there's some algebra you can do. And then you go back to the substituting in. What else can you do? That was what simplify was. It doesn't work here, but it works if you have polynomials. And behavior modeling, okay? You cannot forget everything we've done in the last 5 months, okay? It all builds. The AP exam will assume that you remember everything you've done in the 8 months preceding it. So if I substitute in, and my h goes to 0, if c has to be between x and x, what does c have to be? X, okay? So we know that c has to be equal to x. So once again, I come back over here. My capital df dx is then going to become f of x when I evaluate that limit. So what this tells us is that d by dx of my integral from a to x f of t dt is going to be equal to f of x. All right, so we got it. Okay, so did anybody have trouble with problems from the journal 3, 9, or 19? This is for 6.4. We could certainly do number 19. In fact, let's do the examples I was going to do in class, because there's one that's very similar to number 19, and then you could try it on your own at home, which I think would be good. So let's try a simple one, which is probably similar to number 9. And then we'll do number 20, which is a more difficult one, but that should enable you to work on number 19. Okay? So let's start with page 306, number 10. So what are we supposed to do here? Okay. So if we're supposed to find dy dx, then we're supposed to find d by dx from 6 to x squared cotangent 3t dt. So this does not quite look like the fundamental theorem of calculus, right? If this was just, here, we'll go over here for a minute. If we were finding d by dx of 6 to x cotangent 3t dt, what would that be by the fundamental theorem of calculus? Fundamental theorem of calculus says as long as this is a constant and this is an x, then what do I do? It's this part that I'm taking, okay? So I'm taking the derivative of the integral from some constant to x of f of t dt, and what's that equal to? F of x. So I take whatever my function is in here, and I just change all the t's to x's. That's what the fundamental theorem of calculus tells you. So if this were just an x up here, what would this be? Yeah, cotangent 3x. I would just take whatever my function is in here, and I would change all the t's to x's. Alas and alack, that's not what we've got. We've got an x squared up here. So we're going to have to do something different. Anybody have an idea? No. I mean, I could, but it's not really going to help me because I can't take that x squared and turn it into anything else. Priya. Not exactly. The fundamental theorem of calculus very specifically says that the upper limit has to be an x. Or let me put it to you this way. The upper limit has to be a variable to the first power. What was one of the ways we used to take derivatives? Like, yes. So, like, if you had to take the derivative of that, yeah, but before you could do that in your head, what did you have to do? Ew. We used the chain rule. Very good. No, we're not going to use the definition. But we used the chain rule. Okay? And I'm incredibly proud of you that you didn't need to use the chain rule and you could do it in your head with a group effort. But we could use the chain rule. So that's what we're going to do here. All right? So I'm going to change this. I'm going to let u be equal to x squared. And then I can let y be the integral from 6 to u, cotangent, not cost, or cost, cotangent 3t dt. No, it's not cheating at all. But remember that what I want is dy dx. And a million years ago, when we would take the chain rule, we would take dy du times du dx. And that's what Casey and Zoe did between the two of them. Zoe took the dy du, and then Casey had the du dx. Little group action there. Okay. So dy dx, when I take d by du of my y up there, d by du, now, lo and behold, I have a variable to the first power, which means that I can directly apply the fundamental theorem of calculus part 1. And when I apply the fundamental theorem of calculus part 1, what do I get? Cotangent, but yes, you have my syndrome because I kept wanting it to be cosine. Okay. Because when I've got this thing to the first power, I just take whatever my function is, whatever my integrand is, and I substitute in all the t's for whatever that variable is up there. So my dy du is going to be cotangent 3u, and then what's du dx going to be? Well, I have to take the derivative of this, right? Yeah, 2x. So if we write it again, as always, remember to substitute back in for your u, and I'm going to put my 2x in front because I don't like there to be any question of whether that's a coefficient or whether it's part of what I'm taking the cotangent of. Okay, makes sense? Of what's inside, yeah. We learned it for a reason. All right, so now let's move on and do number 20. And we're still supposed to find dy dx. But now y is equal to this. Okay, so neither of the limits are a constant. Did we spill or just tip over? Okay. Because it's not Zoe's water bottle. If that had happened to Zoe's water bottle, we would have had water all over the floor. Again. So neither of those limits is a constant. Neither of them is an x. So we're going to have to play around with this a little bit. Now, Zoe, your idea before of partitioning is really the way to kind of start this. I'm going to pick some random point A, as long as it's in the middle, and break this into two integrals. And I can do that. Yep, so the second one is already a constant to something, but is the first one. So what am I going to have to do to the first one? Think about your properties of integrals. Yeah, I can flip my limits and put a negative sign in front. And of course, because you all know that I despise integrals, or I'm sorry, not integrals. I love integrals. I despise negative signs out front because you never know if it's really a negative sign or if it's a straight line, especially when everybody takes notes on their computer. Oh, you know how that annoys me. It's got to be 0 points so that we all understand what that means. Oh, I'm just saying. Laziness does not get us anywhere. How much time are you going to spend explaining to somebody that you did not squash a fruit fly on your paper, but it is in fact a decimal point, whereas if you put the 0 in front of it, it would not have been a problem. Did you not see the Muppet movie? When they want to buy the car and the car is like $1,500 or something, and the guy smashes the bug, the big monster smashes the bug between the 5 and the first 0, and now it's a $15 car instead of a $1,500 car. No, it was a movie. So, decimal points are important. Now what am I going to do? Yeah, now I'm going to use the chain rule. Okay, so I'm going to break these down and just treat them separately. So this is going to be y1, and this is going to be y2. So y is going to be y1 minus y2. And then dy dx is going to be dy1 dx minus dy2 dx. Okay. Just because it's easier than doing both of those parallel going all the way down. All right, especially because we're going to have to use different substitutions for each one. All right, so let's start with y1. So y1 is that integral from a to cosine x, t squared dt. As you guys were so quick to pick up on, if I don't have a simple x as my upper limit, I just need to use the chain rule. So I'm going to rewrite y1 as the integral from a to u, t squared dt, and then u is going to be equal to what? cosine x. And then du dx is going to be equal to what? I'm going to take the derivative of the cosine. If you're in so much pain that you feel like death, Casey, we will forgive you. Okay. So when I take dy1 dx, I'm going to get dy1 du times du dx. It's not as bad. You just needed to realize that you had the information. They're not even tricks. It's just you had to put a whole bunch of stuff together. So when I take the derivative here of y1, now, actually, I'm sorry, I'm taking that with respect to u. Now when I take it, I've got a variable of integration that's just to the first power in my upper limit. What? It should be a u. It should not be an x. I may have messed up on the last one. So what's dy1 du going to be? Well, let's just call it u squared for the moment. Let's take it step by step. I'm just going to take my upper limit of integration and substitute it into my function. Du dx, as we already figured out, was negative sine x. So dy1 dx is going to be u squared, and u was cosine. So it's going to be cosine x, quantity squared, minus sine x. Multiplied by negative sine x. That's why everything has parentheses around them. Okay. And then we need to do y2. And y2 is the integral from a to sine x, t squared dt. Sari, what's the first thing I need to do? U equals sine x. Y2 is going to be that integral from a to u of t squared dt. Yep, du dx is going to be cosine x. So now dy2 dx is going to be dy2 du times du dx. And when I take d by du up here, my variable of differentiation, my variable in the upper limit of my integration all agree. The variable in the upper limit of integration is raised to the first power, so I can apply the fundamental theorem of calculus. And so what do I get for dy2 du? Well, let's do u squared. Okay, du dx is going to be cosine x. And then u was sine x, so I'm going to substitute in. I just want to try to get this all together before the bell rings. Okay. And before I have to blow my nose again. Okay. So now we got to go all the way back to the beginning. And dy dx is dy1 dx minus dy2 dx. And dy1 dx was minus sine x cosine squared x. And dy2 dx was cosine x cosine squared x. Okay, so we made it. I have a few more problems that I wish to do tomorrow, so we will finish up this section tomorrow. Please try number 20, and if you can't do it, let me know. Oh, I'm sorry, number 19. Yes, we did just do number 20.